Hello, this video I would like to introduce the 3-5 optical quantum dots. My presentation can be divided into the following parts. First, I will give an overview of quantum dot, including basic properties and talk about what is different of 3-5 semiconductor and why we use them for optical quantum dots. Then I will go through some typical applications of 3-5 quantum dots, including quantum dot qubits for quantum computing, quantum dot lasers, quantum dot light emitting diode, and quantum dot solar cells. Finally, I will briefly talk about the future directions. Quantum dots were first discovered by Russian physicist Alexei Akimov when he was synthesizing nanocrystals of copper chloride and then of cadmium selenide in a molten glass matrix. He observed a fluorescence and a gradient of colors. Because of the average radius of the copper chloride and the cadmium selenide microcrystals are nearly proportional to the heating time. Then he got the size dependence of the absorption spectra. Quantum dots are also known as semiconductor nanocrystals and artificial atoms due to its size and discrete energy levels. The typical size of a quantum dot is usually 2 to 10 nanometers in diameter and contains 100 to 100,000 atoms. And it is much smaller than a human hair. The discrete energy levels come from its ultra-small size. The movement of electrons in a quantum dot can be compared with an electron in a potential well with the width of d, which is the diameter of the quantum dot. The size of the quantum dot changes the energy level. The smaller size means the more discrete energy level of more discrete energy levels. The first energy level of the valence band and the conduction band increases or decreases respectively, which finally leads to the increase of the band gap. That is why the color of the emission and absorption spectra of the quantum dot depend on its size. We can also use the semiconductor with different band structure to create core-shell quantum dots. 3 cases can be distinguished, including the dominated type 1, reverse type 1, and type 2 band alignment. In the former, the band gap of the shell material is larger than that of the core, and both electrons and holes are confined in the core. And in the second, the band gap of the shell material is smaller than that of the core and dependent on the thickness of the shell. The holes and the electrons are partially or completely confined in the shell. In the latter, either the valence band edge or the conduction band edge of the shell material is located in the band gap of the core. Upon the excitation of the quantum dot, the resulting staggered band alignment leads to a spatial separation of the hole and the electron in different regions of the core shell structure. So what is different of the 3-5 semiconductors? Semiconductor compounds can be divided into the 3-5, 2-6, and 4-6. Common 3-5 semiconductors include the gallium nitride, gallium phosphide, gallium arsenide, indium nitride, indium phosphide, and indium arsenide. And among them, the most commonly used one is gallium arsenide. So why we use the 3-5 semiconductors? So most important reason is most of them have direct band gap and high optical and static permittivity. In the direct band gap materials, for example, gallium arsenide and indium phosphide, radiative recombination occurs rapidly and efficiently via a simple two-particle process. Direct bandgap materials have the structure in which the lowest energy point of both the conduction band and the valence band line up vertically in the wave vector axis. That is, they share the same crystal momentum. This is the principal reason why gallium arsenide, indium phosphide, and gallium nitride-based materials have been dominant material systems for the semiconductor diode lasers since their first demonstration in 1962. Then we talk about some typical applications of the 3-5 quantum dots. The first one might be using the quantum dots act as the qubit for quantum computing. Here is an example using an external RF field to manipulate the spin of qubits and realize a coherent rapid oscillation via the RF magnetic pulse. And for the optical system in 2007, optically generated quantum entanglement between the two confined electron spins were realized. The electron spin in the two separated indium gallium arsenide quantum dots can be flipped by the optical signal via a Raman scattering process with the amplitude of the square root of p. The entangled state can be generated by tuning the phase difference between the two optical passes. And now the quantum dot lasers. The germanium layer is reduced the amount of these locations between the layers and the substrate and therefore reduce the threshold of the laser. As we can see that the lasing mode occurs when the drive current is above 100 microampere and around 1300 nanometers. Similar to the quantum dot laser, the quantum dot light emitting diode, also called QLED, is also implemented without the cavity of the mode selection. The emitting wavelength is around 1200 to 1300 for the indium arsenide and gallium arsenide quantum dots. The applications on solar cells are also reported. Here we give an example of the three layers indium arsenide dots spaced by the strain compensation layers, similar to absorption wavelengths. Similar absorption wavelength is obtained around 1300 nanometers. And finally, here is my summary of the presentation. Apart from the applications mentioned above, 3-5 optical quantum dots can also be used for bioimaging, photodetectors, and so on. For there are really a broad range of applications. Future directions may depend on the current research area where it applies for. For the quantum computing regime, higher entanglement rate and individually controlling the qubits are recommended. And improve the facet quality or reduce the dislocations can also reduce the non-radiative recombination centers to enhance the efficiency of the device, like the lasers and QLED. Other aspects may not have been mentioned in this paper may also need concern, such as the synthesis and size the composition of the quantum dots. And here are what I would like to present today. Thank you.